you. So we have one more talk. You may have heard through some of the previous talks, speakers referring to Metaflow hosting, which is not something in open source, but it's similar to what Bento ML would do that has been described as well. So Shashank will, from the Netflix Metaflow team as well, will describe what Metaflow hosting is and how we use it. Thank you.
Hi, so I'm Shashank, and we have talked a lot about Metaflow hosting in previous talks, like Aliki's talk mentioned how they use or leverage Metaflow hosting in order to do predictions for their DSC projects. And then we also had the Amber team, that is the Media ML team, talking about how they leverage async hosting for async endpoints for computing Amber features. And we are just going to talk about the infrastructure behind Metaflow hosting in this talk. So the first question is, why do we need Metaflow hosting? And yeah, so when you think about machine learning at Netflix, the first thought that comes to your mind is recommendations or predicting or finding out which movie a user would want to watch. And there is indeed a lot of research or machine learning being used to do the same, but this lies directly on the consumer side of inference. Metaflow hosting, on the other hand, is used for internal use cases. It's based on a Python hosting model that is Flask framework, so it's definitely not meant for consumer scale models. The places where Metaflow hosting is useful is for internal UI tools like identifying the quality of network or performing machine translation for subtitles, stuff like that. And this is where Metaflow hosting comes into play. The other reason why we need Metaflow hosting is that there's a lot of difference in what data scientists expect the code to be and what infra teams need to provide them. So there's this nice cartoon or comic about every cloud architecture in big techs. You have like these cool databases and then the mismanaged services or like the unmanageable services. And there's also your good old data lakes, which sometimes leak and lead into a data swamp. But the point is that as a data scientist, you don't want to interact with all of this. All you care about is train a machine learning model, write some simple code, and then when actually you deploy a model, you want to do some request tracing and be able to debug your model easily. On the other hand, the infra teams care about some aspects mentioned here, such as load balancing, scaling, and an infra team might also care about like how do we bake the Docker images, like how do we configure the gateway so that the endpoints are routed correctly, and what's the underlying infra for the infra team within Netflix, such as are we using Kubernetes or are we using EC2, S3, and so on. So Metaflow hosting kind of tries to reduce this gap between the infra teams and data scientists by providing a simple mechanism for data scientists to define services which they can then use to deploy their machine learning models or any arbitrary REST endpoints. So what is Metaflow hosting? Before we go with that, I am assuming that a lot of folks are familiar with Metaflow, but maybe some aren't. So at a high level, a Metaflow is just a simple class which represents a DAG. Each function or step is what we call it, represents a node in this DAG. And you can use this DAG to execute code in containers, or you could also execute it locally. And Metaflow internally, as well as an open source, provides a lot of features. Like you can schedule your flows across orchestrators. Like in OSS, you can schedule flows in Argo. On the other hand, we have some internal orchestrators like Maestro within Netflix. And then for each of these steps, you can also specify the resources. Titus is just an orchestration platform we have within Netflix, which is based on Amazon EC2 as well. So the other important thing to note is that each step in your Metaflow flow can generate these things known as artifacts, and these artifacts can then be used in your deployed models. So the way a deployed model can make use of artifact is shown here. This is the entirety of code that a data scientist needs to write in order to deploy the service across multiple instances, have load balancing, as well as proper request tracing and observability metrics. So you have the example web service defined which inherits a particular class, and you can specify the resources needed as well as the auto-scaling params like minimum or maximum instances. Then you can use this function called initApp to initialize your application with whatever relevant models you need, or you could also specify if you need some particular package. Finally, we have this @endpoint decorator where you specify the name of your endpoint, followed by accessing the artifact. So this artifact could be a machine learning model that you just trained via a Metaflow flow, like shown in the previous slide. And in this function, you have this request dictionary wherein you can get the JSON body for your HTTP request and then run your model on it to get a response. And deploying the web service is just as easy as running this command wherein you specify the flow that you want your service to be associated with and the definition of your service. Metaflow hosting provides a lot of features, like this is what I mean by simple definition and simple deployment. There's also the notion of dependency management where you can specify the environment name, and that basically installs the relevant pip packages or conda packages needed for your service. We support auto scaling, which is like scaling according to the number of requests. There's versioning, traceability, and support for async requests. So this is what a deployed model looks like. You have the model deployed across multiple instances at the top. When you make a single request to an endpoint, you can trace the request via Elasticsearch indexes, and we also support tracing via Edgar or Zipkin. You have logging via Radar, wherein you can see how your service is performing with respect to the status codes. And finally, you have the good old metrics, which you can use to find out the status of your service, whether it's up or not. And this is actually used by us to do the auto scaling as well. Like if we see a lot of requests coming in, then we have a job or a service which can auto scale your service. So moving on to implementation details, there are multiple ways of implementing a Metaflow hosting application internally, but there are pros and cons for each of them. So we considered DNS redirection as one of the options, but we want to look at all of these options based on these 4 criteria. Consistency simply means that when you deploy a new version of your service, the redirection should be able to properly redirect to that latest version of service. And this is an issue with DNS redirect because it's based on a caching mechanism, and if you just deployed a new service, the cache would not be updated immediately. And if the user makes a request to the latest version of endpoint, they might still be routing the request to an older version. The other criteria we are interested in is low maintenance. And that's particularly important for us because we are a small team and we do not want to maintain the infrastructure for a lot of services. So while proxy server and OpenFast both support a lot of these features, OpenFast was the best for us because it's low maintenance, because there's another team within Netflix maintaining it for us. And then there's some other features like logging, tracing, and load balancing, which is supported by both of these. And for those unfamiliar with OpenFast, OpenFast is an open source framework for like serverless functions, kind of functions like AWS Lambda, but in open source. This can be based on any backend, so you could have Kubernetes as a backend, or in our case, we use Titus as a backend. Titus is also another orchestration platform within Netflix. So yeah, we chose OpenFast for our Metaflow hosting implementation. The Metaflow hosting implementation consists of 2 main aspects. One is the control plane, and one is the Metaflow client or the container. So the control plane itself is written in Go. It's highly performant, and it is responsible for creating the instances for a new service And control plane is also the service which routes a query from the user's machine to a particular microservice or endpoint. The control plane also does other fancy stuff like generating a swagger for the user, and it's also responsible for maintaining state of the world. By maintaining state of the world, we mean that it needs to know which versions exist right now, which versions can be deployed or undeployed, and which version corresponds to the latest production version. On the other hand, we have Metaflow client and containers, which is the code that the data scientists actually interact with. So the Metaflow client essentially downloads and packages the user's code within a Titus instance, and then it fetches the relevant artifacts, like I mentioned earlier. We then do some user-directed initialization and dependency management, that is, download the relevant packages. And finally, we serve the HTTP endpoints using Flask and F-Watchdog. And F-Watchdog is also based on Go in order for it to be a simple server that is highly performant. So going over this quickly, like we have an OpenFast gateway, which we fondly call Barkley internally. And based on this gateway, we create another service called the control plane that I mentioned in the previous slide. And then this control plane interacts with a RDS instance, which is a database which stores the state for all our hosting functions. And let's go over the deployment path. So when a user deploys a new service, we first go to the OpenFast gateway, which then makes a call to the control plane. The control plane then fetches the relevant information from the database to find out whether the service has already been deployed and we're deploying a new service, or whether we want to create a completely new service. After that, the control plane returns back to the OpenFast gateway, which interacts with our orchestration platform to actually start the services needed. On the other hand, we have so this is what finally deploys the hosted microservice, and you can have multiple instances of the same. Now, going over the query path, if read hastings wants to query a particular endpoint within our hosted application, the query first goes to the gateway, which again goes to the control plane, which uses the DB to route it to the appropriate endpoint, goes back to the gateway again, and then actually makes the call to the microservice or the hosted front end. And finally, we get the response back. So that's Metaflow hosting at a high level. And then we continue developing Metaflow hosting internally. Like one of the features that was added recently was async hosting, wherein you can have long-running jobs. So in general, Metaflow hosting supports a request for a period of 20 minutes. But with async hosting, we support jobs that can run for as long as 12 hours. This is particularly useful for the media ML team because they run inference on movies, which are pretty large or long and take a long time to perform, to execute. And the reason for the 12-hour time limit is because of the SQSQ, which is what we used in our implementation. And this is an example of how you can use polling to get the response from an async request, but you can also have a simple callback function to do whatever you want. And one of the latest features that we integrated into the Metaflow hosting pipeline is adding support for a GraphQL backend. Why do we want support for GraphQL backend? At a big company like Netflix, you can have multiple microservices owned by different teams. As a client UI engineer who defines or creates front ends, you don't want to make calls to like 10 different microservices in order to get the response for making a UI page. Having a federated GraphQL edge allows you to make one single query, and then this federated gateway allows you to route the queries to the appropriate microservices, get back the responses from each one of them, it collates them, and then returns a unified response back to the client UI engineer. So in order to support a federated gateway, we recently added support for defining a GraphQL backend in Metaflow, and it's pretty seamless for a user to add this. There is literally no change in their service code. Like the service code remains the same, except Within their endpoint, they can define the name for the GraphQL endpoint, as well as the input type and output type. GraphQL is a typed language, unlike Python, so you need to define the types like here, and then we do all the associated stuff like deploying it to the federated edge. And that's it. Any questions?
Thank you.